Yeah, so today we're going to be talking about something. I have maybe the longest title at the conference. I put basically every word I know in there. But at a high level, what we're going to be talking about is the journey that we at Memfault have gone through with a lot of our on-device coredump processing. I'm going to kind of walk you through a lot of the structures of an ELF coredump and how we've changed the processing. Before we do that, a little less interesting, some stuff about me. Like I said before, my name is Blake Hildebrand. I'm a software engineer at Memfault. Kind of a lot of the background I've had is kind of gone through the whole of the tech stack. I started out doing microcontrollers, Cortex-M stuff at Garmin, mostly for fitness watches, so board bring up, focusing a lot on the Bluetooth audio setup for the first audio watches there. Oh, that kicked on at a weird time. Then I kind of switched to doing embedded Linux and microcontrollers at Amazon Robotics, working on a lot of their autonomous and safety systems. Then I took a bit of a switch and did a lot of back-end and distributed systems work at AWS, focusing a lot on their the indexing and metadata service for S3 OneZone. They kind of kept telling me I was a bit too grumpy though, and kind of, it's like, who is this guy? Like, why is he always so grumpy? And then I decided to come back and be with my fellow grumpy people, embedded software engineers, and that led me back to Garmin, where I work on Memfault D, which is back to Memfault, developing Memfault D, which is our daemon that runs on device, connects metrics, crashes, logs. But we're going to be focusing on the crash section of that today. So kind of overview what we're talking about today. The big thing is we're going to look at ELF coredumps, what they're made of, and kind of the different steps we've gone through. We started off kind of doing a normal pass-through, just collecting coredumps as they exist already from the kernel, shrinking down the size a bit by trimming off everything but the stacks, and then doing the real fun part, which was my giant clickbait article title, was to kind of do the unwinding side of this on device. So kind of a little reminder of like where we're trying to get. We want to see a stack trace. Like we want to go from what is essentially a big blob of memory that the kernel hands us and get this, which is actually useful. We can see what happened at the crash. But why do we care? There's plenty of other good methods to capture crashes out there. There's Sentry, there's BreakPad, there's all this nice stuff. Why are we reinventing the wheel? Well, we're focusing on being embedded first. There's a lot of unique problems that come with capturing coredumps on embedded devices. You could have very little storage. Depending on how much memory you use, a coredump could be very large. You could be on a metered connection. So maybe you have enough storage, but you're paying per byte that you send over the wire. So you don't want to send a very big one. And your connection might be inconsistent. You could be on a device that moves around. Maybe it goes underground. Maybe it just goes to an area that doesn't have cell service. So we need kind of a way to capture that and push it up later. So let's kind of talk about what is a Linux coredump? What does it consist of? Well, it's really just like a snapshot of memory at the time of crash. It's written as an ELF file, and it can be loaded into GDB, and it allows you to kind of inspect that crash as if you had a debugger attached at the time of the crash. So it's very useful for when you've shipped something out into the field. Maybe you didn't write quite as many unit tests as you should have, and now it's crashing. What do? You don't want to wait for some customer or end user to let you know that it's crashing. They might not even know that it's crashing. It could be very different. So we can load this right into GDB. I have a very stupid program that just dereferences a null pointer, and we can see that we can get a backtrace from GDB with this. So I keep saying things like crashes. Like, what does that mean to crash? And what does it mean from the perspective of the kernel? Well, a crash is going to be anything, obviously, that causes your program to halt unexpectedly. And from the kernel's perspective, it's going to get a signal that's going to tell it what to do. I said complete signal list. They're not actually here. It wouldn't fit on the slide. But the signals here tell the kernel to basically dump memory out. to however you have it configured. So how are you going to enable them? A couple kernel configurations. These are going to be on most precompiled distributions by default. And if you're using Yocto, it's usually a default in there as well as build root. You also need to make sure you set the right resource limits. If it defaults to typically a fairly small number. We have an unlimited here for our purposes, but overall, you're just trying to potentially maybe limit the size of a core dump that comes out. The real interesting part of like how you're kind of configuring these core dumps is the core pattern file. This is in sysfs, and it tells you basically where you can write the core dump to. So you've got a few options. First one, pretty straightforward. You can write straight to a file. There's a bunch of different arguments you can pass there that the kernel knows to set. So for this instance, we're grabbing the process name, the PID, so that we can have these core dumps be unique per process as they happen. And then the more interesting thing we can do is we can actually tell the kernel to pipe all of everything that it would be writing to that file into the standard in of a program. And this kind of sets the stage for most of what we're going to be doing. We can do a lot of interesting things with this. We can intercept this data as it comes in. We can look at procfs, which will be mounted for the entirety of the stream's uptime, as well as until the handler itself exits. And so we can look at things in there, add it to the core dump, manipulate some things. All right, so kind of looking at what the ELF file layout looks like for a core dump. It's really kind of a subset of what you would expect for typical ELF files. You're only going to have really a few things. You're just going to have program headers and then a bunch of segments. And there's really only two segment types you're going to see for the most part in a core dump. It's going to be the note segments and the load segments. Note segments are going to have metadata that you would expect. We'll use a lot of that later on as well, but think things like current process state and a few others. And then load segments are literally just address ranges of memory as it's currently mapped. So this is where your stack memory is going to be, your heap memory, and any other memory that might be currently mapped to the process. Note layout is pretty straightforward. You've got sizes for your name, which is just a string saying, what is this? It's like a friendly name for the note. And the description size. The description size is basically, it's kind of a bad name, but it's really the binary blob that makes up your note. So the note field is pretty freeform. It can be, sometimes it's just a raw C structure. Sometimes it might be formatted in BSON or CBOR or something like that. But the type kind of dictates where you're going to be parsing. So you'll read the type, and then you know what you need to parse. All right. There's a lot of rambling about ELF files, so we'll actually talk about what we did with them. So the first thing we kind of did is pretty straightforward. We're kind of in a mostly pass-through mode. We're adding a single note to the ELF file. We're really just trying to set the stage for future improvements and add some metadata like software version, hardware version, things like that, so that you can identify the device that caused the crash. So our approach is exactly what I said. We're just going to get that core pattern. We're going to pipe into the core handler like we looked earlier, and we're going to copy over the note segments. We're going to be streaming all that data, avoiding the allocations and all that fun stuff. Yeah, so it's all right there as well. So this is kind of what we end up with. It's not too special, right? It's basically the same thing. And you might be asking, why did I do this? Did I convince my manager to let me go on a fun ELF file vision quest? Maybe. That might have been part of it. But also, we kind of look at all these benefits. We talked about the metadata injection. We have this future flexibility where we've now got this ability to take in this core dump data and potentially do something with it, something that we'll talk about in a second here. But we're also kind of avoiding big allocations. If you've got camera data, or if you're running one of these big crazy LLMs on your device, you're going to be allocating a lot of memory. And that memory is all going to show up in the core dump. And so we want to make sure we're not doing extra allocations. We're copying directly from the memory to the file so that we're not taking up even more memory. So I've probably hinted at it several times here, but like, what is the problem here? Well, the problem is size. Like, they can be really, really big. Obviously, it's all dependent on the program that you're running. The biggest thing that's going to be taking up space is heap allocations. So if you're not using the heap too much, maybe they're not that big, but a lot of people are using the heap, so it gets pretty big. All right, a brief detour. I bet you guys thought that title was all clickbait. It's only mostly clickbait. We're going to talk a little bit about Rust. So why did we move from C to Rust? Our initial coredump handler was written entirely in C, and it makes sense to reach for that, right? We're a bunch of embedded engineers. We've all got decades of C experience between us. Why wouldn't we reach off the shelf and grab that? And we did, and it worked great for a while, but as we kind of started to work on more stuff and add features to this, it started to kind of creak and groan a little bit. And we had kind of some trouble doing that. The biggest thing is that we're doing a lot of messing around with memory. We're moving things around, we're accessing pointers, and so we want to make sure that we can only have to worry about those type of safety issues and let Rust handle everything else. There's also a lot of things we can use in the ecosystem. We're parsing ELF files, we're parsing dwarf information. And while there are good libraries that exist for that in C, the packaging kind of becomes difficult. We're trying to deliver something that can be easily installed, easily compiled. And as soon as you kind of start bringing in that other stuff, do you have submodules? Like, how are you linking this all together? And it works if you're using a build system like Yocto. You can kind of define those dependencies, but it gets a little harder when maybe someone is just loading this onto an Ubuntu or Debian image. How do we make it easy for them? And some of this stuff too is like, could we have written some of this in C? Definitely. Did I want to do that? Also probably. Would I have time to do that? Probably not. And also there's kind of just a lot of ergonomics that come with Rust outside of the memory safety and the ecosystem. It's just a fun, expressive language to use. So, it's just more fun. I guess that's subjective, but the last one is clearly all the cool kids are doing it, right? Tyler, if you're watching this is only mostly a joke. But yeah, it definitely, that definitely has an influence, but I can't admit that to my manager. But I just said it out loud on a recording, so sorry again. If you're a C head, you're probably looking at this and like, what the hell is that? Honestly, if you're a Rust head and you're looking at this, you're also probably saying, what the hell is that? But we kind of, if you think about what our core handler is doing, it's taking in a lot of data from different sources. We're reading from procfs, we're taking from standard in, we're reading from proc maps. And so there's all these different things, and that kind of makes it hard to test because we're reading from all these files, all these different input streams. Going this semi-crazy route with generics, we can write really expressive unit tests by either implementing these traits on a test device. Actually, what ends up happening is that we take a normal coredump file, and we just wrote a little wrapper that kind of reads it and puts it into all these different streams for us so that we can test this on representative data and not have to worry about, does this have the current procfs mounted for this PID and all that fun stuff. And last, I kind of mentioned, just like a shout out to some of the libraries we're using. Clap is great for CLI management. We're doing a lot of dwarf processing. Gimli has been great. And ELF processing, Goblin. It's funny, my wife saw me making this slide, and she was like, do you really use all these words in your job? Like, this is, this is kind of silly. She was like, I don't know. I'm really into Lord of the Rings, so she thought I was like making a fan website or something. I don't know. Cool. All right. So back away from the clickbait part of the presentation, back into the meat. So we're going to kind of go on an adventure here to slim down the size of our core dumps. And like I mentioned before, what we're going to do is only capture stack memory, which is kind of true. We'll get a little more into the details in a second. But as I mentioned before, you might have limited space. You might be on a metered connection. And so in either of those cases, you don't want to be spending a lot of time. You can kind of think of us as like hanging out on your couch a little bit. Like we're there to help, but you really don't want us taking up a lot of room. And like if you look at me, like I'm kind of big. If I'm on your couch, I'm taking up a lot of space. The nice part about core dumps is like we can chop them up to make them fit in small places. Please don't chop me up to make me fit on your couch, but if that's what you're into. So kind of what I mentioned, what are we going to strip down to? I said stack memory, but there's a little bit more. There's some information inside the core dump that is neither stack information nor heap information. That's kind of things that the debugger uses to figure out the state of the program. Things like dynamic libraries and little bits of info about frame data. And so if you think about every dynamic lib you've got linked, we need to know not only where that is, where it's mapped in memory currently, and things like build ID. So let's go in here a little bit. And so if we talk about what exactly we're going to capture here, we're going to just capture the top in bytes of each stack. We're going to completely get rid of the heap allocations, and we're going to capture that metadata. What are the trade-offs here? Well, you're not going to have any heap allocated values. So if you've got like a big string that you allocated and the pointer to it's on the stack, it's not going to show up in the debugger. And you're going to have some limited stack depth here. Obviously, you could configure it to capture a really big part of the stack, but if you're trying to optimize for size, you might only get the top 4 or 5 frames. But in general, we found this to be pretty acceptable. Most stack traces are really debuggable just by looking at the trace alone. Like you can see where you crashed and see the line number, and you look at that, and most of the time you're like, oh, I know exactly what went wrong here. Excuse me. And on top of that, most stacks aren't that deep. A lot of the times, well, I don't know, maybe you're making really deep stacks. Maybe that's a generalization, but most stacks just aren't going that deep, and really it's the top few frames that are the most interesting, because that's really showing where you're crashing and how you got there. All right, so how are we going to find these stacks? If you remember, we kind of had this layout for the ELF file. What we kind of need to do is we need to know 2 things. We need to know the current state of the general purpose registers at the time of crash, and then we also need to find the stack segments themselves. So those are going to be all the load segments. Luckily for us, we mentioned kind of these note segments before. One of the more important parts of this is the PR status or process status notes. This gives you a view into what was going on the process at the time of crash. And particularly the spot that is most interesting is that PR reg member, which is the general purpose registers. Obviously, that's going to change from platform to platform. It's going to be a different set of registers, but the general idea is the same. We need that stack pointer. So what are we going to do? We're going to find the stack pointer for each thread, and then we're going to go into proc maps, which is basically in procfs. It's showing you all the different map sections of memory, and we're going to find out which one of those maps has the stack pointer in it. From there, we can know, hey, this is the stack segment. We kind of have to go on this little search for it because they can be labeled, but it's not always accurate. Sometimes you'll see something labeled as a stack, and it's only the stack for the initial thread. So if you're spawning multiple threads, they might not be labeled, so we can't really depend on that. But once we've found that segment, all we have to do is start at the stack pointer and then copy up or down, depending on which way your stack is growing, and copy either to the end of the segment or the max number of bytes you have configured. And then boom, you've got your stack memory. The next thing we have to talk about is kind of that debugger information I mentioned earlier. So the big problem here, like I said before, is dynamic linking. You've got a bunch of dynamic libs linked into your binary, and they can just be loaded into different spots in memory. And we need to know, one, if those libraries are actually part of this, and 2, where they are. With address space layout randomization, which is basically putting your program in a random spot in memory every time it runs, It's a nice security feature, but it does make our lives a little harder. Because it's, you're changing the address every time, so we need to basically get that runtime address and convert that down to what is expected inside the file. So this is where we've got a very helpful little friend here. We've got our debug structure. This kind of gives us two things. This tells us which file is, which library is linked, where it's linked, and yeah, and that's kind of what we get from there. Oh, I went the wrong way. So we know that we want it, but like, where is it? Well, that's where we kind of come back to where I lied a little bit. I said there's only these notes and load segments. There's one more that we have to kind of worry about, and this is the dynamic header. This kind of tells us where these dynamic sections are mapped inside of memory. And so we need to find that, iterate through all the dynamic sets, because the way it's set up is it's just a linked list, and so we have to go find every dynamically linked library, look for that structure tag that we wanted, and then extract it. And then we just need to make sure that we copy that memory range to our end coredump. So what do we need to grab for each of these mapped files? We need to make sure we grab the elf header, which is going to be loaded into memory, all of the program headers on there, and the build ID note, because we still want to be able to, if you're running something like, I'm blanking on the name, the thing that fetches symbol files based on build ID that I can't remember the name of that I should. Debug info D, thank you, Pat. So if you're running something like debug info D, you need that build ID to be able to fetch that debug information, because most of the time you're not going to have that loaded on device. So when we later on do some processing of this coredump, whether it's in GDB or some other program, you are going to need to be able to find the symbol information. And so we just kind of go back to our trusty procpid maps, iterate through all those ranges that we got before from our debug, and we can find each one of those ELF files as it's mapped in memory and make sure to save off that just as well. So it's a lot of rambling to get to what did we get here. So this is the original size of kind of the slightly modified ELF file. This is a pretty small program, so it's not particularly large. It's just a Rust program that has a main and a few functions. Only thing it's linking is libc. And so we see it's pretty large. I mean, you think 2.6 megabytes, you might not cough at that too much, but some people, that's pretty large. And we've seen coredumps up into the hundreds of megabytes, so they can get very large depending on your use case. The optimized coredump, much smaller, 75K, about 35 times smaller. And this is useful too. You might just say, well, why not compress it? Compression works generally pretty well here, but it can be kind of random in nature, because depending on the state of your program, the coredump is composed mostly of just memory. And so if you have a program that's running and it's not just like all initialized to zeros and you've got a lot of values in there, it's not going to compress that well because it's going to be fairly randomized data. So we don't see a lot of consistency across compression, so we're definitely just trying to get it as small as possible. So what's the end impact here? Store multiple coredumps. You're not transmitting as much over the wire if that's something you're concerned about. And we're doing it all on device and maintaining full debug capability. Full is maybe a bit of a stretch there because you don't have your heap values, but like I said before, not super useful. All right, I've talked for 24 minutes and we've finally gotten to the title of the talk. So this was kind of the next step we had, is that we've also seen a lot of people making embedded devices really concerned about privacy. If you've got a device that a person is directly interacting with, they might write things down in it, and it might be stored in memory. And if you're working with, or if you're ever trying to like certify a device to be compliant with those type of things, you might think like, well, you probably already accomplished this with the previous setup, because most of this data, if it's a string or something like that, it's probably going to be on the heap. If you've ever talked to a lawyer about this, they're going to not be as happy about the idea of like, I'm pretty sure we're sending customer data. That usually doesn't fly with them. So you kind of need to erase all sense of doubt. And so how can we do that? Well, kind of as I mentioned before, we can do a lot of the unwinding on device with the end goal of sending up just the program counters for the stack trace. It's going to mean that no sensitive data leaves the device, and a nice side bonus is it's going to be even smaller than the coredumps that we looked at before. So just a quick reminder, this is where we're trying to get, right? We want to get a stack trace, but the big change here is going to be that those locals on the right won't be present anymore. So when we think about what a debugger does when you're loading in a crash, there's kind of two parts to it. If you call backtrace and see the backtrace, what is actually happening is first it has to reconstruct the frame data. Remember before that the coredump is just a big blob of memory in a file, and the debugger needs to figure out what did your frame look like. So it has to start at the stack pointer from each thread and kind of unwind, which is the name of it, unwind and go backwards through each of those and reconstruct each stack frame. Then from there, once it's got all the memory addresses, it can grab the debug info from all the various debug sections that are usually loaded into an ELF file and get you your nice names. You can see your local variable names, see your function names. And so what we're going to do is we're going to do half of that on device. We're going to do the unwinding of the stack, or of all the stacks, on the device. And we're only going to send up the program counters and some of that metadata that we talked about before. And so with that kind of setup, you can be pretty sure there's no sensitive data coming off the device because it's just addresses of functions, essentially. So what's the information we need? Like I said before, we need the program counter for each frame. And then we need a lot of that info that was contained in the DT debug section, or DT debug struct that we talked about before. We need the PC range for each function. So we need to be able to find if the function is inside of a dynamic lib. We need the build ID for not only the main binary, but all of the other linked libs. And we need those compile time and runtime offsets, like we talked about before, to account for ASLR. And we need the file path as well, because you might be doing it with the build ID, but you might be loading this locally, so you might want to be able to just use the file path to find everything. And so, yeah, as I kind of mentioned before, ASLR presents a challenge here because we're going to have these addresses, all the program counters on the stack and everything. They're not going to be what is represented inside of the actual executable. So when you go to load that into your debugger, we have to do some translation to what was the address in runtime and what is the address as expected by the file. So this is kind of what we're trying to get to. This is the end range, right? It's a little simplified. I took a lot of it out of here. But we're trying to get a few things. We want to know the PC range for each either main binary or dynamic lib, and all that we talked about. And then finally, we have the threads at the bottom with all the program counters for them. So if we're talking a bit about unwinding, we need to kind of think a bit about what it looks like to unwind data. This is kind of a really simplified view of what your stack might look like. You've got your stack pointer and then the base of your frame. And on there, you're going to have different registers mapped. So in this case, I've got the link register R0, R1. It could be all of them. It could be none of them. And then you're going to have your local variables. So what we want to get to here is really the top part. We're not looking at the local variables at all. So we're just trying to reconstruct at each frame, what do all the registers look like? And I know some of you probably like there's a frame pointer. Like, why are you doing all this? Well, some platforms don't have frame pointers. And even the ones that do, if you look at the default arguments for 01 on GCC, the frame pointer is omitted. And it's omitted because you can get a general purpose register back from it. And that's pretty good. Getting a whole other register you can use for calculations, that's definitely an improvement. But so now how do we get this? Well, we can look at the exception frame section that exists by default in most compiled programs. It comes in by default with GCC and LLVM. A lot of you probably strip it out because it's sometimes pretty big, but it's much, much smaller than the debug information. And so what this does is it contains a bunch of rules that we can do to rebuild the frame. And those are rules for each register, as well as things like personalities for different languages. You think like if you're doing like constructors in C++. But luckily, since we're not doing local variables, we can just ignore all that and just focus on the registers. So what are the key components of the EH frame? A lot of three-letter acronyms on here. Some of them look like government agencies, but they are actually just kind of describing the stack, or the frame. The big one to talk about here is kind of the canonical frame address. If we think back to our stack frame example, this is kind of the equivalent of the frame pointer. This is telling us where does the current frame that we're looking at start. And it's going to be the source kind of looking at relative to that frame pointer, where are all of the registers at. So here we can see this is just a dump using readelf. This is a very simplified example, but this is kind of a rule telling us two things. It's telling us on an x86-64 platform, where is the stack pointer located at, and then where is the instruction pointer. So we can see that start off, the stack pointer, the frame address is just offset from the current stack pointer by 8. And so we can kind of get that frame address and then know where the register is based on that frame pointer. So kind of saying again, that's how we get the frame address, the frame address. And then all of the register rules are generally going to be relative to that frame address. So we'll be kind of going through those and recreating those for every frame. And so we look here, we see a nice little fun ASCII art kind of showing what that looks like. So we've got the stack pointer. Right above that, you've got I added a little bit of flavor here, but you've got the instruction pointer. And then you've got any more saved registers that might exist in a more complicated example. All right, so now we need to finally grab our thread information. It's going to be pretty similar to what we looked at before. It's the process status note, and we're going to get the GP registers for each, do the same thing. We'll go into the maps, look at all of these different runtime addresses, and then we're going to find everything we wanted. So kind of reiterating, what do we need? Well, we need those EH frame and the EH frame header, which I haven't really talked about, but is basically just a lookup table into the EH frame. And then we need build ID and our runtime versus compile time offset. So we've got it, we found all that. Let's run through a really basic example and kind of see what we have. So first we need to, for each thread, we need to find GP registers, search inside the EH frame or EH frame header, go through all of those rules to reconstruct the registers, and then what we want to do is use the LR, or in platforms like x86-64 where there is no LR, they create like a virtual address that's just return address. And we use that for the PC for the previous frame. And then we also use the canonical frame address as the SP, the stack pointer for the previous frame. And if you think about how that's stacked, I probably should have a picture here, but the frame address is really going to be the stack pointer for the previous frame because that's going to be where that stack frame ended. And we'll just keep repeating that until we get to the end of the stack. So it's either going to be the end of the segment, or a lot of times the EH frame will have a kind of indicator that you've reached the end of the stack. And so here we can kind of see the top part of a final example. We have a signal, we've got the command line that caused it, the PC range of the binary, and then that build ID and offset information that we needed for it. And kind of a truncated stack trace here as well because it didn't quite fit. So then let's talk about the final step. We've got this nice little JSON blob, and it needs to be processed. So we receive it up on the cloud, or you could do this locally on your machine as well. You have to find the symbol, so that's either from the address or the build ID, get the symbol file, adjust for ASLR, and then just run through address to line, and you can get each one. So here's step one. We know that the top of the stack, so this would be the stack pointer, is inside this range, so we know it's in this trigger coredump program. We're going to take that address and subtract the runtime offset, add the compile time offset, and then we will have the address as is expected to be in the compiled file. And then finally, we resolve the symbol. So if we look here, we just have address to line, and we're passing in that address, and we see that that null pointer dereference that I did earlier. And so it looks exactly the same. So that's just kind of running through again what we get here, but the end result is that we get this full stack trace without sending any memory up to off the device. So you can guarantee that nothing's left, and it's going to be smaller. So yep, as you can see again, nothing leaves the device, no stack variables, nothing is sent off, and it's much smaller. It's 35 times smaller than the previous example and over 1,000 times smaller than the original. So you're definitely running through this. You're making some trade-offs, but at the end, you're getting the same stack trace information without having to take up a lot of size or really risk leaking any customer data. So kind of in conclusion, coredumps are powerful. They can be huge. Stack-only coredumps definitely get us down in size, but we still have that kind of that worry about customer data, and then finally doing the on-device unwinding, we get an even smaller coredump and less or no risk of leaking customer data. All right, yeah, if you want to check out the source code for this, it's on the Memfault GitHub. Also, if anyone wants a free beer, we'll be having a happy hour tonight on, man, I practiced reading this like 4 times, 5430. It's very weird to have number and then spelled out number. 5430 Rooftop. And this whole presentation was on our blog Interrupt, so if you want to read this and not listen to me drone on for 37 minutes, you can scan that QR code and look at my author page. And that's it. Thank you.